The famous physicist and Nobel laureate Richard Feynman once said, "No one can understand quantum mechanics, you can only get used to it." Today I'm going to show you how this abstract and obscure theory of physics evolved into two major technological revolutions. The second one we are just in the middle of. So, what is quantum mechanics? Don't worry, I'm not going to give you the course I'm giving once a year to my students. But let's try to illustrate a few basic principles by an example given by another famous physicist, Erwin Schrödinger. He wanted to envision the obscurities, the strange things of quantum mechanics by a cat. So he imagined this imaginary experiment. Don't worry, it never happened in reality. He put a cat inside a box together with a radioactive atom. Now, one thing you should know about quantum mechanics, if I was a quantum mechanical, meaning if I was very, very tiny, I could have stood on that side of the stage and at the same time also on the other side of the stage. The same thing can happen to the atom in the box. This is an atom that can emit radiation, but it can be both in a state where it radiates and in a state where it doesn't radiate. Schrödinger envisioned an entrapment inside the box. The radiation emission triggers a hammer to fall on a vial full of poison, and when the poison is released, the cat is dead. Now, because the atom is both in a state that emits and does not emit the radiation, this process, this chain of events, both happening and not happening, and the cat is both dead and alive. Now, did anyone here ever saw a cat which is both dead and alive? Schrödinger neither. So he said, so what will happen if we open the box? And the answer that quantum mechanics gives us is that something will happen, something will change. The cat that was before both dead and alive now will be classical, will be only dead or only alive. So you should ask, so what will it be? Dead or alive? And quantum mechanics tells you the outcome will be random. If we repeat the same experiment many times, sometimes we'll find out the cat alive, sometimes we'll find out the cat dead. So this randomness and all the other weirdnesses of quantum mechanics was very strange to the scientists at that time, and even another famous physicist, Albert Einstein, he didn't like this concept, and he phrased his famous quote, "God does not play dice." Today, by the way, we know that Einstein was wrong. God does play dice. So all of these weird ideas were formulated during the 1920s and 1930s. Later on, in the 1950s and 1960s, two new technologies emerged that created what we call today the first quantum technology revolution. And as I said before, I'll show you later that today we are in the middle of the second quantum technology revolution. So what were the technologies that led for the first quantum technology revolution? These are very famous. These are the transistor and the laser. So you may have heard about them. Transistors are in the basis of any computational device we are using today, may it be a computer, a supercomputer, or even the smartphone in your pocket. It's based on transistors. Now, the laser serves for many, many technologies, but maybe the most important one is what creates the light that transmits information over the internet today. So all the internet is based on laser technology. These two technologies led to what we called, and actually was mentioned in the first talk today, the information revolution. And here in the picture you see the server farm of Facebook. It combines both technologies. First of all, the servers are computers based on transistors, and it is connected to the internet to spread information, to distribute information with the light of lasers. And I don't have to tell you how much it affected our life, this revolution. Okay, so what's led to the second revolution? This is a basic understanding. All the systems that carry information today comply to classical physics. Some examples are hard drives. They contain information, they store information in magnetic media. Magnetic, classical physics. Same goes to disk on key, flash drives, they store information with electrical charges, computer memory, store information with electrical currents, but also, as I mentioned before, optical fibers that carry information, the information is carried with light, again, classical physics. But then there's a question. What will happen to everything we are used to do with information if instead of storing it in classical physical systems, we store it in quantum systems, such as atoms, single atoms, or photons, or other devices that are listed there? What will change in the ways we treat information, we transmit information? And the answer is the essence of this second quantum technology revolution. It's based on 3 pillars. The first one is devices, machines that will calculate, process information in a new way. If the information is in quantum systems, we call them quantum computers. Second thing is what will happen if we transmit information, which is quantum mechanical, and we get new protocol for transmission. I'll tell you about them in a moment, and we call this quantum communication. And the last one is the way we are sensing the environment. If we treat the information we collect from the environment as quantum information, we can do things with more accuracy, less resources. One example I put here is what are called LiDARs, light-based radars, which are the basic technology behind autonomous cars, but there are other examples like MRI machines that will benefit also from these technologies. Because these technologies are so basic, emerging, revolutionary, interdisciplinary, many at the end, at the Hebrew University, we were the first in Israel to establish about 10 years ago the Quantum Information Science and Technology Center. It's a center that combines more than 20 researchers from different departments. You can see some faces here on the board that work together, publish works together, collaborate. And today we are just going to build a new home, a new building for this Quantum Information Center. So why are quantum computers that I just mentioned so strong? Why are we so excited about them? So there are many ways, and again, it will be a much longer talk than you would like to if I tell you all the details, but just to understand the essence. A classical computer can take one input, one question, process it, and give you the output, the answer to this question. Now, if you have another question, you have to refeed it and reiterate and repeat that process again and again. A quantum computer is working on a quantum system, and if you just recall, a quantum system can be in a few states at the same time. So I can feed a quantum computer with many inputs at the same time, many questions together, and have it process them all in one go and give me all the answers to all these questions at the same time. Of course, I'm oversimplifying things, but this is called parallelism, and it gives strength to quantum computer to solve some problems much, much faster than classical computers. Some of these problems, for example, will enable the design of new materials. It will enable large corporations to optimize their process, their operation more efficiently. But on top of many benefits that humanity will get from quantum computers, there are also some risks. And one of the major ones is this. Today, when you communicate over the internet and we would like to transmit some secret message, if something is secret and we would like to keep it confidential, we use cryptography to encrypt the data which is transmitted from side to side. This cryptographic protocol, this encryption, is based on hard mathematical problems. It happens that these hard mathematical problems are just hard for classical computers, and quantum computers will solve these problems very easily, making this secrecy obsolete. Actually, a quantum computer can decrypt all the information which is secret today on the internet. Moreover, it's not just that quantum computers can break these encryption protocols. There are already known organizations today that are storing information that we are transmitting over the internet, just waiting for the time that quantum computers will be big enough. We already have some of them, but they are too small for that. But we are waiting for the day in 5, 10 years when they'll be sufficiently big enough and crack this information in 5 years or in 10 years. Now, there are a lot of secrets that we would like them to be secret now, but also in 5 years or 10 years and even more. So today already, there is a risk to data, and that triggered the NSA to issue a warning 3 years ago, already 3 years ago, for organizations that have critical information to prepare for the post-quantum computing era. Because of this threat, me and my team established a new company called QuantLR that will deliver a technology to encrypt information, to keep it secret over the internet, that cannot be hacked using even quantum computers. It's based on a physics principle instead of the hard mathematical problems, because as I said, mathematical problems are hard to solve, but actually quantum computers can solve them easily. But physics is impossible to break. In order to break this protocol, you need to change the laws of physics. You need to change quantum mechanics. And this, as we expect, will not happen. Because this technology called quantum key distribution is so strong against quantum computers, data that you transmit today using this technology will be never hacked. Even in 100 years, if you can imagine the strongest ever quantum computer that will be developed, it will not be able to hack these secrets that we transmit today using this technology. And because of that, organizations that will adopt this technology now will not have to upgrade their equipment in the future. Moreover, another risk that exists today is that if someone is stealing your information today, you'll not be aware of that until they use the information and do you harm. But in this technology, remember the cat is changing, the quantum cat is changing when you observe it. If someone is trying to eavesdrop, he is actually checking the state of the cat, changing it, and this change is detectable. So we are aware of the tampering attempt right when it happens, and the protocol adapts to it to keep what it's called the ultimate security level of the protocol. There is another use for this technology called authentication. Sometimes what we communicate doesn't have to be secret, but it's very important to know that whoever sent the information is really whoever it says is. Imagine that I would like to issue, I just read today that the USA controlled some power plants in Russia. So imagine I would like to issue a command to a power plant of another country to shut down. This is not a secret, right? The message contains no secrets. But the power plant would really like to authenticate the message and know that whoever issued the command is certified, is qualified, authorized to give the command. These methods of communication today are also secured by the same mathematical problems, and therefore they are vulnerable for quantum computers. And our technology, quantum key distribution, the technology of QuantLR, can also serve there. So the addressable markets, as you can imagine, are government secrets, the finance industry, medical information. The European Union just issued last year a new order that medical information has to be kept secret for more than 40 years, at least 40 years. Data centers, data is stored in data centers, but they keep backing it up between data centers all day long. So it's on transit, it's vulnerable to attacks. 5G networks, the next generation of cellular phones, are being started to be deployed today. They are going to use a huge amount of fiber optics backbone, and this is again vulnerable. And they also claim that they are going to increase security in this new standard, so we fit just in the right place. And as I said, critical infrastructure. To summarize, today we are standing in the middle right now of a new technological revolution. It's going to affect our life a lot, for the good and for the worse. We have to prepare for it, and it's the goal of the Hebrew University to be the spearhead of this new technology. Google just recently conducted a survey, worldwide survey. How many people are trained, certified to work only in the quantum computing industry. They discovered that the answer is between 900 to 1,000 worldwide. I estimate that in Israel the number is less than 50. It's clear that the mission of the Hebrew University should be to train this next generation of scientists and engineers so we can really lead this field. Thank you very much.